This is our last unit of the semester. Okay, we need to make sure that we understand graphing. You will be graphing a lot in IM 3, not necessarily quadratics, but the concept's the same. So, all semester we've been talking about quadratics, right? We've factored, we have taken square roots, we've used completing the square, all of that stuff, right? And we gave you this form. What's the name of this form? Standard form. Okay, so this is standard form. What makes it a quadratic? What makes it a quadratic? The x squared. Your highest exponent is a 2, which makes it a quadratic. We also talked about function notation, f of x. Who remembers what that also means? Or what it's the same as? Y. F of x is the same as y. Typically when we're in function notation, that means we're plugging something in to get another value. Okay? Now, all of our graphs for this entire unit will be parabolas, which you saw on that Desmos activity. What shape was a parabola? A square? Okay, so a U, right? So our parabola, our graphs are going to be parabolas, and they're going to look like U's. So you're going to have one that potentially looks like this, that faces up. And you're going to have one like we saw in the Desmos activity that potentially faces down. Okay, it can go in either direction. If your parabola faces up, it is positive. And if it faces down, it is negative. And specifically, it's your A that's positive or your A that's negative. Now, in that Desmos activity, we talked about that peak point, right? The highest point that the ball went. There's a name for that. And for all these parabolas, it's known as the vertex. Okay, so that peak point is going to be known as the vertex. So here, it's not a high point, it's a low point, right? So this wouldn't necessarily model me throwing a ball, but it's the low point. And if something's the low point, I'm trying to figure out how to phrase this to get the answer that I want. If something's a low point, can you go any lower than that? No. So what's another word of like, I can't go any lower, that's it?
Maximum. Minimum.
Minimum.
Oh my God, I said that. Minimum.
Okay, it's the minimum value. So if your parabola faces up, you have a low point, and that is your minimum value. Now, if I have a parabola that was modeled like in that Desmos activity where my vertex is now a high point, what can you say? Maximum. It's the maximum value. Does that make sense? Yeah? Okay, so you have a minimum and a maximum. Now, we also talked about, in that last slide, what our graph looked like. So I threw the ball, or the person threw the ball, it went up, it hit that maximum point, and then it dropped, right? But what did that curve look like? Amelia, I think, said it. What did you notice about that curve? It's a reflection. Is there another word that we can think of that would work?
The mirrored image.
It's a mirrored image, okay. Now mine's sketched right now. But we have a line through the vertex that is known as the axis of symmetry. which means on either side of the vertex, my graph is exactly the same. It's symmetrical. It's a reflection. It's a mirror image. So if on one side you have a nice curve and on the other side you don't have the same curve, you did it wrong. Okay, it should be exactly the same, where if you fold along that line, along that vertex, it will match up on both sides. Now, I told you it's a line, and everyone can see that it's a line, right? The axis of symmetry. We'll get into it, but our equation for that line is going to be x equals some number. Okay? And we'll see it on a graph, but it's x equals always. X equals some number. Do you remember domain and range from IM1? A little bit. Does anyone remember what the domain is? What the domain is?
Oh, wait, like I remember, but I need to be reminded.
You remember, but you need to be reminded.
I know.
Okay, so your domain is all the x values. So your domain is going to be all the x values. For every single parabola that we're going to deal with, our domain is always all real numbers. And you can write it like that. Okay, so your domain is all of your x values. It's always all real numbers. And let's think about why that's the case. So if you put one of these parabolas on a graph, why is it that it's all real numbers? Why do you think it's all real numbers? Why is it all the x values? What hints at that it's all the x values? We're going to come back to this question. So keep that question in your brain. What do you think the range is? So if the domain is all the x values, what do you think the range is? All the y values. Now the range is something that we have to think about every time. So again, every single time, our answer for domain is all real numbers. You don't have to think. Your range we have to think about. And here's why. Depending on if you have a maximum or a minimum, what happens to all the values? Like if I have a high point, right, here's my high point for y, what happens to all of these values? Are these larger than this one or less than this one? They're less than, they're all the smaller y values. But if I have a low point, what are all these values? They're greater. So, we could have two answers. Y is greater than a number. Is that going to happen when we have a maximum or a minimum? Are all the y values going to be greater when there's a maximum or a minimum? Minimum. It's backwards. So if you have a minimum, it's going to be y is greater than whatever that minimum value is, greater than or equal to. Or we're going to have y is less than or equal to a number. And when's that going to happen? When are all the y values going to be less than our value? When it's at the top, so when it's a maximum. I have to figure out where to put this. I want to add a word, and we're going to call it orientation. Orientation. And it kind of goes with this first part here. Orientation is when your graph opens up or down. And we'll look at the A value to determine if the graph opens up or down. If A is positive, it's going to open up. If A is negative, it's going to open down. But you're going to see the word orientation, and that's what it's talking about. Whether it opens up or down. There's a lot of vocab right now. So far, so good? Are we okay? All right. So let's look at this first graph. This first graph is known as our parent function. It's like the starting point for all of the other graphs we're going to deal with. It is our parent function. Now, if I know standard form is ax squared plus bx plus c, can you tell me what a equals? What does a equal? 1. Right? The number in front of x squared is 1. So our parent function is when a equals 1. On Friday, we created a table of values. Can we do the same thing with this function? Yeah? So let's plug it in. So I have negative 2 squared. I'm going to rewrite my function so I have it. What's negative 2 squared? Positive 4. Okay, I'm going to plug in negative 1 squared. What's negative 1 squared? 1. I'm going to plug in 0 squared. What's 0 squared? 0. What about 1 squared? 1. And what about 2 squared? 4. Do you notice anything about that table of values? There's a pattern? Is that what we're going to say? They're all positive? Okay, it won't necessarily always be positive, but in this case they are. What kind of pattern do you see? Like, don't tell me the numbers, but do you notice a pattern? Like, I'm trying to think of how I want to word that. Well, do you notice a pattern without telling me what the numbers are? Like, how does that pattern work? Huh?
The negative x's are like always the same as the positive x's.
Okay. Do you notice that the pattern's around a certain point? Is there a point that changes the pattern? Like, where does the pattern change? So it goes 4, 1, 0, and then 1, 4. So where is the pattern kind of coming back around? At 0, 0. So when we think about that graph from the Desmos activity, we had an arc that went up, we got to the peak, and then it went back down. What was that peak point called? The vertex. So this happens to be our vertex. So it will be symmetrical, or you will see a pattern on either side of the vertex. So let's plot those points. So my first point is negative 2, 4. 1, 2, 3, 4. My second point is negative 1, 1. Then 0, 0. 1, 1, and 2, 4. Now when you draw in this curve, what should the shape be? A U, which means there's a curve to it. It's not going to be perfect every time, but do your best. Okay, so you're going to draw on your curve. We're going to add arrows because it extends on, but it should be a U shape. Can you see now that the vertex is 0, 0? So the graph starts by going down and then curves back up. So my vertex, because you'll have to name every single one of these things. My vertex is 0, 0. It's where it changes direction. Do I have a maximum or a minimum? Minimum. I have a low point. Okay. So I have a minimum. And we're going to identify the minimum value. Your minimum value is always what the y is. So what is my y there? 0. Okay. Your minimum and maximum value will always be the y of your vertex. So in this case, my y value is 0. So maybe we can make a note here. up top. Max/min value is the y of the vertex. That might be helpful. The max and min value is the y of the vertex. I'm also going to name the axis of symmetry. So what did I say the axis of symmetry did? Up here. What do you notice about the axis of symmetry? It what? Go straight down the middle through what? The vertex, right? The axis of symmetry goes straight down the middle through the vertex. And your axis of symmetry is always the x value of the vertex. So the axis of symmetry is the x value of the vertex. What's the x value of my vertex? 0? But remember I said you had to write it as an equation, so it's going to be x equals 0. So once we know the vertex, we can figure out a ton of information. So the minimum value, minimum or maximum values based on the y value of your vertex. Axis of symmetry is always the x value of your vertex, but you must write x equals. We can also name the domain. What's the domain? What's the domain? All real numbers. That is always the answer for your domain. All real numbers. Make a note. That is always your answer. Don't think on that one. Or think too hard. It is always all real numbers. Because my x values continue to increase on both sides, right? They go on forever. My y value or my range, however, changes. So if I look back up here, we said we had a minimum, correct? Which means it's going to be y is greater than. All my y values get larger. Do you see that? So y is greater than or equal to, and it's greater than or equal to your y value of your vertex. What's the y value of your vertex? 0. It can't go any lower than 0. Right? Here's that point, and everything is greater above it. Our vertex literally answered every single one of those questions. So if you can identify the vertex, you should be able to answer all of those other ones. Are we okay with that? Some of us more than others. We're literally doing this for the next 4 weeks, so we want to get real good at it. Can we try the second one? Something's going to change a little bit though. What do you notice about the a value? Our a value in this first one was what? 1. What's our a value in this next one? 1/2. Right? So, when a is less than 1, we are going to have a compression. So let's think about what that's going to look like. So if a is less than 1, and in this case it is, we're going to have a compression. If I take my graph and I press down on it, what's going to happen? Kind of do it this. So pretend this is my graph, and I press down on it. What happens?
It's flatter.
It gets what?
Flatter. Wait,
Okay, so it's getting flatter, but what else is happening?
expanding.
It's getting wider at the
Wider,
same
yeah.
time, right? You see how it's stretching out?
Yeah.
Okay, so if you have a compression where your a value is less than 1, your graph is going to become wider. Okay, so let's see if that actually happens. So let's plug everything in. So f of x equals 1/2 times x squared. We need to do the squared part first. So -2 squared is 4. And what's half of 4? 2. -1 squared is what? 1, and half of 1? 1/2. I'm going to write 0.5 because I'm going to have to be able to graph it. What happens when I plug in 0? 0. 0 squared is 0. 0 times 1/2 is still 0. What happens when we plug in 1? 0.5 again? Which means what should this last answer be? 2. Because it's symmetrical, so let's just make sure. 2 squared is 4. Half of 4 is 2. Now I want you to look at the scaling on this graph versus this graph. What's the scaling on this side? It goes by ones, right? What happens here? It goes by 0.5. Do you see that? So you need to watch the scaling on your graphs as well. So let's plot those points. So -2, 2, -1, 0.5, 0, 0, 1.5, and 2, 2. Did my graph become wider than my original graph? Okay, so when you compress it down, it's going to be wider. So let's see if we can identify all of those features. What is the vertex? 0, 0. Right? It's that where it changes direction. Do I have a maximum or a minimum value? A minimum. And what is my minimum value? 0. Okay, it's the y value of your vertex. Then I have an axis of symmetry, which I did not draw in here. I'm going to draw it in. It's hard to see. But I have a dotted line through the origin. You can't see it at all. But know that it's there. Same thing with this one. What's my axis of symmetry? 0? It's a line. What's my axis of symmetry? X equals 0. X equals 0. What's the domain? All real numbers. Good. That's not going to change. And what's my range? Are my y values getting larger or smaller? Larger. They're going up, so it's y is greater than or equal to 0, which is your minimum value. Now, I mentioned orientation up here, going up or down. Both of these have an orientation that does what? Does it go up or down, your graph? It faces up, right? And what did I say that the up or down was related to? Positive and negative with the a value. What was a here? What did a equal in this first one? 1. That's positive, right? What did a equal here? 1/2. That's still positive, which is why it faces up. What does a equal here? 2. So is it going to face up or down? Up. Okay? But we'll notice that 2 is going to change things. So if A is greater than 1, we're going to have a stretch. So if I take my initial graph and I stretch it up, what's going to happen? It's going to get skinnier. Right? I want to stretch too. When you grow, theoretically, you thin out a little bit. Okay, so here's what I would like you to do. I would like you to fill in the table, and you have 2 times x squared. And I want to see if you can identify as many key features, all these ones that we have, as possible. Okay, so when you go to plug it in, what's negative 2 squared? 4, and 4 times 2 is 8. What's negative 1 squared? 1 times 2 is 2. 0 squared? 0 times 2, 0. 1 squared, and again, because of symmetry, this should be 2, which it is, and this should be 8, which it is. Now, I was asked if 0, 0 will always be our vertex. The answer to that question is no, but right now it is. Okay, we're starting with the basics. So let's see how you did. I should probably plot my points first. How about that? 2, 8, negative 1. Okay, shh. Did your graph become skinnier than the initial one?
Yes.
Yeah. Okay, there was a stretch because my A value is greater than 1. So the vertex is at 0, 0. You have a minimum value at 0. Your axis of symmetry is x equals 0. Your domain is all real numbers. And your range is y is greater than or equal to 0. How'd you do? Perfection. Okay.